right, howdy partners. Western Day, Spirit Week here at the high school, so figured I'd dress up a little right fancy for y'all today. Hope you don't mind. Anyway, today we're going to deal with a concept called the mole, trying to figure out how we take care of counting really large numbers of really small things in chemistry. That's basically the idea, and the idea of the mole. And it's all the fault of this dude over here. Look at that sexy beast, Avogadro. I wouldn't take his number, but look at him. Those eyes. Something's wrong. Anyway, so with this, let's take a look at how we deal with this concept of counting by weighing. So just so you know, there's a second video that comes along with this afterwards. We're going to deal with the calculations more in a minute. This one's more about just kind of the big idea. So I don't know if you've ever looked at a box of paper clips and wondered how they actually got 100 paper clips in there. Is there really 100? What if there's 101? What if there's only 99? Do I get a refund? Is there some dude that's sitting there at the end of the factory going 1, 2, 3, 75, 76, 70, 1, 2, no, there isn't. Same thing, like when I open a bag of chips, the mystery bag, why is there only 5 chips in my bag of chips? Well, it turns out that both of these things, there isn't a dude actually counting out like 1, 2, 3 Doritos, that's all you get. It actually turns out that when we're dealing with, on a big industrial level, when we're dealing with lots of really small items, it's much easier for us to deal with the concept of mass rather than the concept of count. There really isn't a guy sitting there counting out 100 paper clips or 5 potato chips. They do all of these sorts of things with large quantities of things by simply weighing out a set of them and then figuring out, well, on average, how many chips or whatever are in there. With potato chips, by the way, they do it by mass, and then the bag is just by volume, so yeah, it settles, right? That's what they say. I don't believe them. It turns out it's just faster, easier, more efficient time-wise to do this process of counting the number of particles by weighing the total mass and figuring it out. So you've probably seen at one point in time in your life the jelly bean challenge like this, like, okay, how many jelly beans are in the jar? Whoever guesses the closest amount can figure out, and someone's sitting there like doing an average kind of thing, or they're counting the number of jars or jelly beans in a jar, trying to figure out what's in the center. I mean, there's all kinds of crazy stuff. The whole hint here is that if you tried to count them out, counting is slow. Even if you tried to figure out the answer, it would take forever. I mean, look at this dude down at the bottom with his surfboard. I don't know what this guy's hobbies are, but apparently it has something to do with surfing and jelly beans. It's kind of weird. But if you tried to actually count out the number of jelly beans in that jar, it would take forever to do it. It's much easier to do it by the concept of mass. So really, when you want to do this, there's 2 things you need to know. Number 1, you need to know the mass of the whole container. So how much jelly beans are in there in the first place. Yeah, there's a trick then of having to separate the mass of the glass from there. You don't want to include that. But what's the mass of jelly beans in that dang thing? And then number 2, you would need to know the mass of a single jelly bean. And those are really the only pieces that you need. Once you know the mass of one and you know the mass of the quantity, it's a simple matter of basically division to figure out how to get those pieces to go together. You can count by weighing. So here's an example, a little smaller version of it to give you an example of what this looks like. If I have a bag of Skittles, which weighs 61.5 grams, it says right on the label there, how many Skittles can I expect to be in that bag? So I'm going to show you this using a dimensional analysis style. You probably figure out that you just divide it out, but here's what it looks like when we do dimensional analysis. And I'm going to encourage you to use this method because as our problems get bigger and more complex, it's less obvious what you divide by. So like I said, I'm going to kind of continue to use that strategy here. So I would say grab 10 Skittles, throw them on the scale, figure out how much 10 Skittles weigh. I found out that they weigh 11.34 grams. I had a snack this morning, delicious. So that means my average mass of a Skittle is 1.134 grams. Okay, now what? Now we set up our little dimensional analysis little steps here. I'm going to show you the way I'm going to use it in these videos here. It's going to look like a little table like this. So you can kind of imagine that this is my first step, this line right in the center here, this one that I'm kind of arrowing on right here. That's kind of our per line. That's that long line. And then each one of these vertical lines right here would be the separation between the steps. So kind of like the ones that we've done, it just has a box around the outside. So anyway, I'd start here with my total grams, 61.5 grams, my mass of my bag. And then here's my conversion. 1 Skittle equals 1.134 grams. That's a conversion factor. It doesn't sound like it, but it is because I figured out how much 1 Skittle weighs, kind of on average. And then all I have to do is multiply across the top, divide by the bottom, and I get a number that looks like this. Oh, there's my mass conversion. There's my number right there. I get 54.232 plus a little bit more if you look at it on the calculator. So sig figs, how would I round this? Looks like 3 sig figs in our problem. 61.5 has 3 sig figs. 11.34 has 4 sig figs. So I would use 3 in my answer. So 54.2 would be my answer rounded in numbers of sig figs. You can't really have 0.2 of a Skittle, so probably a count would be like, I would guess 54 Skittles is how I would guess that. Okay, so your turn. Take an example here. What if I filled my bag with M&Ms instead? Did you know that M&Ms are a little bit lighter than Skittles? Kind of a weird one, right? So I grab a handful of M&Ms, toss it on the scale, weighs 12.81 grams. Turns out this time I had 14 M&Ms in my particular handful. So how am I going to carry this out? It's a little two-step problem that you need to do. So number one, figure out how much does one M&M weigh. So here's my little conversion right here. 12.18 grams is 14 M&Ms. There's my conversion. If I math it out, I get that one M&M weighs 0.915 grams per M&M. There you go. Then I can use that conversion. So here's my little wonder fraction, the way I'm going to set it up. There's my M&M conversion average mass right there. And if I do the math on there, I get this crazy long number, 67.213, whatever it is, M&Ms would be in there. Sig figs, how many do I have? Looks like 3 to me. 61.5 grams still has 3 sig figs, even though my mass has 4 sig figs. So my answer would be 67.2 M&Ms. They're a little bit lighter, so I have a couple more. And a good guess there would be 67 M&Ms, because you can't have 0.2 of an M&M. All right, so why are we dealing with M&Ms and Skittles and jelly beans in a chemistry lesson? Well, it turns out that atoms are so freaking small, and they're ridiculously tiny, that when we're dealing with quantities of atoms in our chem lab, we're usually dealing with it by mass. I can't have a single atom. Well, I could. I just wouldn't be able to see it. So usually we're dealing with masses of atoms, 5 grams, 10 grams, 15 grams. We can't just dump them out and count them. It would take a ridiculously small tweezers. You couldn't see them anyway. It would take days isn't even enough time, years to count out the number of atoms that would be in there. And our answers just are ridiculously huge. So we tend to deal with a similar kind of a concept of converting from a count of atoms to the average mass of atoms to the grams of an atom. So it just makes a lot more sense to us to deal with this. That's the big kind of idea that I want you to have in there. So it turns out here's our dude, Avogadro. His first name was Amadeo. His parents must not have liked him. Amadeo Avogadro, lovely name. He was working with gases. He actually, this poor guy, his work wasn't even recognized until like 50 years after he published it. Like right after he died, it actually became like, oh, this guy was brilliant. Poor guy. Anyway, he was working with gases, trying to figure out how many particles of gases, basically what we would call molecules today, would be in different volumes. And he kind of discovered this big idea that if you have the same volume, like these balloons, same volume of a gas, it must contain the same particles. He was doing some work with changing the temperature, expanding it, contracting it, did crazy stuff. Anyway, it wasn't until long after his death that they realized that, wait, this guy was onto something. His work could actually answer a lot of our other problems that we're having. In terms of dealing with atomic mass and how many particles are in an average sample of an atom. So again, he wasn't real famous actually this time. He was kind of a sloppy chemist apparently. He kind of didn't keep really good records. Nobody believed his work was that good. But later on, they realized that he had the right idea in terms of what it was. And he was the guy that came up with this concept of there's a count of atoms and it has to do with mass and it has to do with, in his case, volume of atoms. It turns out we now call that number Avogadro's number. It's what we would call a mole as a concept. It's kind of like a dozen. A mole is a count of certain things. A dozen means 12 of anything. Well, a mole happens to mean 6.022 times 10 to the 23rd of anything. Particles is what we would call it. And again, they've been working on trying to develop his number, this Avogadro's number now, for 150 years at least at this point, and kind of trying to get better with it. So this concept, now that we know more about it, is actually the concept that ties together the concepts of mass of an element and the number of atoms in an element. And again, it's taken them a long time to do that because atoms are so small. Here's the big idea. It's in red on your screen. Other than the definition that a mole is 6.022 times 10 to the 23rd particles, big idea. 1 mole of an element weighs its average atomic mass in grams. So if you have a periodic table nearby, you'll see where these numbers come from that are on the screen here. That means if I have a mole of carbon atoms, it weighs 12.011 grams because 12.011 is the average atomic mass of carbon. It's that number on the periodic table. A mole of oxygen atoms would weigh 15.99, almost 16 grams. A mole of hydrogen's a lot smaller, only weighs 1.0078 grams. This is the concept, that's the big idea that tied together his crazy weird number and his ideas about volumes of gases to a number that we use every single day, and that's why this number is named after him. So we call this concept, by the way, molar mass. Average atomic mass of an atom is a mole of that particular substance, so molar mass. So this number is kind of a magic number for us, just to give you kind of a concept of kind of how big or how small this is. You can have a mole of anything. I want a mole of dollars personally, even a mole of pennies. I'd be fine with that. But it turns out a mole is such a big number that we have a hard time quantifying with it. Atoms are so tiny. A lot of times this number is bizarre. Remember how I taught you guys how to do scientific notation earlier? This is why. If you had a mole of water molecules in a tablespoon, that's roughly about a mole of water molecules. And again, just a regular big spoon that you'd maybe eat cereal with at your house. There's enough molecules of water in that single tablespoon to cover the entire state of California in sand to a depth of, I don't know, 82 feet, I think is what I calculated it out. State of Texas, Texas is bigger than California, 50 feet deep. So a 5-story building worth of sand particles has the exact same number, not quite, roughly the same number of particles in it, sand particles, as there are molecules of water in a spoonful of water. I'm going to let that sink in for a second. That's how small molecules are. So when we're trying to deal with chemicals in a little pile of chemicals, the number of atoms in there is incomprehensibly huge. That's why we deal with this concept. So I'm going to get kind of like round up this particular little presentation with kind of an idea of how do we use this in a calculation. Again, the second video that we'll do here has a lot more of these calculations, but how do we do this? So, for example, if I had 25-gram sample of carbon, that's not a very big sample, you can easily hold it in one hand. How many atoms are actually in that gram sample? So here's the two things that you would use for this, and this is that idea that we've got. Two key conversions. We're going to use the dimensional analysis system or method to kind of attack this. The two things that you need is that 1 mole of anything is 6.022 times the 10 to the 23rd items. We're going to deal with atoms in this case, and that works for us. Second thing is we're going to use that concept of molar mass, which is 1 mole of an element, or atoms of an element, is going to weigh that much in grams. So we're dealing with carbon here. You will need to have a periodic table when you're doing these kinds of problems, so I need to know the molar mass of carbon, and that's from the periodic table. We would call it atomic mass if we're just looking at the periodic table. So here's my strategy. Here's how I set it up. Again, this is just an introductory one. 25 grams of carbon. Here's how I set this up. This is what the dimensional analysis would kind of look like. Here's our steps. That first step I'm going to put in there, I'm going to use molar mass because I know that 12 grams of carbon is the same thing as saying 1 mole of carbon. That's what molar mass does for us. It allows us to get to a count. The second step I'm going to do is that last one. That's that definition of what a mole is. I can use 1 mole of carbon atoms and deal with 6.022 times 10 to the 23rd atoms of something. Now you can probably see this is going to end up being a really large number. Multiply across the top, divide by the bottom. How many atoms are actually in a little pile of carbon? 25 grams worth? It's a ridiculous number, 1.25 times 10 to the 24th atoms of carbon. Again, that number of atoms of carbon would bury the state of California in that many, if I had that many grains of sand, would bury the state of California to like 100 and something feet of sand. It's ridiculous how big it is. So again, with this particular concept, this idea of counting by weighing, it allows us to get a handle of how many atoms are in a sample. It's a relatively ridiculously large number that's going to deal with that concept of what a mole is, that idea of 6.022 times 10 to the 23rd atoms equals a mole. And then the second idea is that we can convert from atoms and moles then to grams by using the concept of molar mass. So there you go. An introduction to what a mole is, kind of why we use it, the concept of counting by weighing, simply dividing by average atomic mass, and then being able to convert that into a number of particles, which would be a number of atoms. Luckily, for most of the time, we don't have to do this too often other than this chapter, but the concept of molar mass is actually a big one we're going to use throughout the rest of the year. It's one of the central concepts of chemistry. So if you take a look at the next video, it'll give you some idea how to practice with that. Thanks. Have a good day, and yeehaw, right? Go Vikings.